When installing a 120/208 volt panel and a 277/480 volt panel in a separate building, and both feeds originate from the same main building, it is necessary to ground both panels to a single grounding electrode system at the separate building. This practice is mandated by electrical codes to ensure electrical safety and proper system functionality. The grounding electrode system serves as the primary means of connecting the electrical system to the earth, providing a low impedance path for fault currents. This path facilitates the operation of overcurrent protective devices, such as circuit breakers or fuses, during ground fault conditions, thereby minimizing the risk of electrical shock and fire. The grounding electrode system typically comprises one or more grounding electrodes that are electrically connected to form a unified grounding network. Common grounding electrodes include ground rods, ground plates, metallic water pipes, and concrete encased electrodes, also known as grounds. The selection and installation of the grounding electrode system must comply with the requirements outlined in the National Electrical Code, specifically Article 250. It is crucial to establish a robust and reliable grounding connection to safeguard personnel and equipment from electrical hazards. The grounding electrode system must be properly sized and installed to effectively handle the anticipated fault currents. The size of the grounding electrode conductor, which connects the panel's grounding bus to the grounding electrode system, is determined by the size of the largest ungrounded conductor feeding the panel, in accordance with NEC Table 250.66. This conductor must be sized to adequately carry the maximum ground fault current that could occur. The grounding electrode conductors must be securely connected to the grounding electrodes using approved methods such as exothermic welding, listed connectors, or other suitable means. The connections must be mechanically strong and electrically conductive to ensure a reliable grounding path. When multiple panels are installed in a separate building, all panels must be connected to the same grounding electrode system. This can be achieved by running a common grounding electrode conductor from the grounding electrode system to each panel's grounding bus. Alternatively, a grounding busbar can be installed in the separate building and connected to the grounding electrode system. Each panel can then be connected to the grounding busbar via a separate grounding electrode conductor. The grounding busbar provides a convenient and effective means of interconnecting multiple grounding conductors and ensuring a common grounding point for all panels. It is important to note that the grounding electrode system must be installed as close as practicable to the separate building to minimize the length of the grounding electrode conductors. The shorter the grounding electrode conductors, the lower the impedance of the grounding path, and the more effective the grounding system. The grounding electrode system must be accessible for inspection and maintenance. The location of the grounding electrodes must be clearly marked, and the connections must be protected from corrosion and physical damage. Regular inspections should be conducted to ensure that the grounding connections are intact and that the grounding electrodes are in good condition. In addition to the grounding electrode system, it is also necessary to provide equipment grounding conductors within the branch circuits that feed the electrical equipment connected to the panels. The equipment grounding conductors provide a lower impedance path for fault currents from the equipment back to the panel, facilitating the operation of overcurrent protective devices. The equipment grounding conductors must be properly sized and installed in accordance with NEC Article 250. The size of the equipment grounding conductors is determined by the size of the overcurrent protective device protecting the circuit, in accordance with NEC Table 250.122. The equipment grounding conductors must be connected to the equipment grounding terminals of all electrical equipment, such as receptacles, lighting fixtures, and appliances. The connections must be mechanically strong and electrically conductive to ensure a reliable grounding path. It is essential to maintain continuity of the equipment grounding conductors throughout the branch circuits. The equipment grounding conductors must be connected to each other at all junction boxes and other points where the conductors are spliced or terminated. The connections must be made using approved methods such as wire connectors or grounding screws. It is also important to ensure that the metal enclosures of all electrical equipment are properly grounded. The metal enclosures must be connected to the equipment grounding conductors to provide a low impedance path for fault currents. The connections must be made using approved methods such as grounding screws or bonding jumpers. In summary, when installing 120/208 volt and 277/480 volt panels in a separate building fed from the same main building, grounding both panels to a single grounding electrode system at the separate building is essential for electrical safety and proper system functionality. The grounding electrode system must be properly sized, installed, and maintained in accordance with the National Electrical Code. Equipment grounding conductors must also be provided within the branch circuits to ensure a low impedance path for fault currents. By following these guidelines, you can create a safe and reliable electrical system that protects personnel and equipment from electrical hazards. The NEC, or National Electrical Code, provides a comprehensive set of standards and guidelines for electrical installations. It's updated regularly to reflect new technologies and safety practices. Article 250 within the NEC specifically addresses grounding and bonding requirements, and it's essential to be familiar with this article when working on any electrical system. Grounding and bonding are two distinct but related concepts. Grounding refers to connecting an electrical system to the earth, providing a low impedance path for fault currents. Bonding refers to connecting all metal parts of an electrical system together to create a common electrical potential. Both grounding and bonding are necessary to ensure electrical safety. The purpose of grounding is to provide a path for fault currents to flow back to the source, allowing overcurrent protective devices to operate and clear the fault. Without a proper grounding system, fault currents could flow through unintended paths, such as through a person's body, resulting in electrical shock. The purpose of bonding is to minimize voltage differences between metal parts of an electrical system. Voltage differences can create a shock hazard if a person comes into contact with two metal parts that are at different potentials. By bonding all metal parts together, the voltage difference between them is minimized, reducing the risk of electrical shock. The grounding electrode system is a critical component of the grounding system. It provides the connection between the electrical system and the earth. The grounding electrode system typically consists of one or more grounding electrodes that are electrically connected together. Common types of grounding electrodes include ground rods, ground plates, metallic water pipes, and concrete encased electrodes. Ground rods are typically made of copper or copper-clad steel and are driven into the ground. Ground plates are typically made of copper and are buried in the ground. Metallic water pipes can be used as grounding electrodes if they are in direct contact with the earth for at least 10 feet. Concrete encased electrodes, also known as UFA grounds, are made of a bare copper conductor that is encased in concrete. The size of the grounding electrode conductor is determined by the size of the largest ungrounded conductor feeding the panel. NEC Table 250.66 provides guidance on sizing grounding electrode conductors. The grounding electrode conductor must be sized to adequately carry the maximum ground fault current that could occur. The equipment grounding conductor provides a low impedance path for fault currents from the equipment back to the panel. The size of the equipment grounding conductor is determined by the size of the overcurrent protective device protecting the circuit. NEC Table 250.122 provides guidance on sizing equipment grounding conductors. The equipment grounding conductor must be sized to adequately carry the maximum ground fault current that could occur. Bonding jumpers are used to connect metal parts of an electrical system together to create a common electrical potential. Bonding jumpers must be sized in accordance with NEC Table 250.102. The bonding jumpers must be sized to adequately carry the maximum ground fault current that could occur. When installing electrical panels in separate buildings, it's important to consider the grounding requirements. If the buildings are served by the same service, the grounding electrode system at each building must be connected together. This can be achieved by running a grounding electrode conductor from one building to the other. The grounding electrode conductor must be sized in accordance with NEC Table 250.66. If the buildings are served by separate services, each building must have its own grounding electrode system. The grounding electrode system at each building must comply with the requirements of NEC Article 250. It's also important to consider the bonding requirements when installing electrical panels in separate buildings. All metal parts of the electrical system in each building must be bonded together. This can be achieved by running bonding jumpers between the metal parts. The bonding jumpers must be sized in accordance with NEC Table 250.102. When working with electrical systems, it's important to follow all applicable codes and standards. The NEC provides a comprehensive set of guidelines for electrical installations. By following these guidelines, you can ensure that the electrical system is safe and reliable. It is crucial to consult with a qualified electrician to ensure that the electrical system is installed correctly and safely. A qualified electrician has the knowledge and experience to properly design and install electrical systems that meet all applicable codes and standards. Working with electricity can be dangerous, and it's important to take all necessary precautions to protect yourself from electrical shock and other hazards. Always turn off the power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment, such as safety glasses and gloves. If you are not comfortable working with electricity, it's best to hire a qualified electrician to do the work for you. Remember, safety should always be your number one priority when working with electricity.